Okay, section 15.4 for us in this class deals with, it depends which class you take. Calpoly, that's 15.4. Pasadena, that's 15.3. In general, it's the double integral in polar forms. So suppose we're given r equal f of theta, and we want to find the area that I shaded. If I just focus on that area, what we do, we break this into smaller areas. Remember, polar runs in circles, right? You rotate and you run toward or away from. So if I take one of those and I look at that, it looks like this. This is the change in the radius. That's simply whatever this r is minus this r is. And I'm trying to find the area of that piece. And I'm calling this the ith piece in there, if you might. Well, recall, if I'm looking at a sector, I know that if this is S equal r times theta, and in this case it turns out to be that right there. So if I want to find the area, I would say the area is really length times width. I could say that's the length. The width is really, if I take this and I stretch it in a straight path, it's S. S equal the radius times, and isn't this right here d theta? So a sub I would be really r sub I dr d theta. So what this means, if I want to find the change in area, what that area is, that is really r dr d theta. And if I take the double integral over region R of f of x, y, dA, which is what I did in the previous section. Well, let's see how this works. I need to know what this angle is. And I need to, actually, let's go this way. Let's say this is alpha, and let's say this is beta. That's going to be the integral from alpha to beta of f. My x, if you recall, is r the cosine of theta. My y is r the sine of theta. My dA, which is a big deal, if you are converting, is r dr d theta. So you pick this extra r every time you transform the double integral, and r runs from, depending what you want, assuming we just want to find a certain area. Let's say, I should have did that from the beginning. You could say 0 in this case, but if you really wanted to go from, you don't want to find the whole thing. You just wanted to find this area. Kind of like just this area. Again. So if it runs from 0, it's really straightforward. That runs from the origin. But if I really take my arrow, r runs from A to B, whatever that is. And that would be my conversion. And that's pretty much all there is. identical to what you did in your previous course when we went to polar in one dimension. But when I say one dimension, I mean a single integral. So we're going to start by taking on all different combinations. A rectangular region R is given. Oh, how did that shift that way? I didn't see that. I meant for this to be at the origin. Somehow it shifted off. That's okay. We can fix that, right? We can always fix things. Here we go. So, if I want to use rectangular and polar coordinates to find that integral, well, if I decided to really use this, I would really go for rectangular coordinates if it was up to me. So I would say x runs from 0 to 3, right? And y would run from 0, and that line is raised since that's 3, 3. That line right there is simply y equal x. And I know if I don't write anything in there, leave it as a 1, that's the definition of area. If I want to use polar, again, if it's really rectangular, you should go for rectangular, r d theta. Well, theta runs from 0. If you have y equal x, that's really pi over 4. And do you see how the arrows run? You're going to look, we did this in single integral by running. We're running to this line. R runs from 0 to this line. The line is really x equal 3, but x is r, the cosine of theta equal 3. Divide both sides by cosine. Let me get a bit more space. We have plenty of room, no need to squish anything. Actually, I could write it here. X equal 3, but x is r, the cosine of theta. Divide both sides by cosine because you want r. And isn't that 3 the secant of theta? And there it is. That would be my area using polar. Now, if I have line segments, that is pieces of lines, I really should stick with rectangular. But I could do every problem using both notations if I really want. Now, looking at example B. If I want to use rectangular coordinates, this is half a circle really. So I would say the double integral will be the integral, and let's see, I'm going to run x from -2 to +2. And I'm going to run y from 0, and this is x squared plus y squared equal a 4, so y will equal positive the square root of 4 minus x squared. And you know if you're going to integrate this, you're going to have to use trig substitution. You're going to let x equal twice the sine of theta. Do you remember that? That's a lot of work. Instead, if it's pieces of arcs, I'm better off using polar coordinates. Theta runs from 0 to pi. That's simple. And always remember, there's an extra r. r d theta. Well, r is going to run from the origin. Do you see where you're running to every time? This is much easier to do than this. It doesn't require you to use trig substitution or anything like that. Bottom line, you need to be able to do the problems both ways. Can you tell what this is finding? So again, we map this kind of sort of on this graph. It says, sketch the region whose area is given by the iterated integral, and evaluate the integral. I'm assuming you could integrate easily, and I'll show you really quick how we do that, but, you know, if I wanted to sketch the graph, that's the main point that I have. Can you sketch the graph of what this represents? So that turns out to be the tough part, because you're going to have to go backwards. Well, theta runs from 0 to pi, so this is only in quadrant 1. That's good news. Pi over 2, that's what I mean. And r runs from 0, from the origin, to r equal 3 the cosine of theta. What is that? That is r equal 3 that is r squared equal 3r the cosine of theta. That is x squared plus y squared equal 3x. Now, of course, you don't have to do that because we know this is a circle with, I just need to center that better. We know that's a circle, center at the origin, with a diameter of 3. And how do we know that? Because we did polar already. We know they're talking about this circle. So we know what they're talking about in this case is really this piece of the graph, where that is 1, 2, 3. If you're going to convert every time, you're going to spend a lot of time doing that, but we know what that looked like already. And how about here? And if I wanted to really figure out what they're talking about, they're saying theta runs from pi to 2 pi, pi to 2 pi, so I'm here. R runs from 0 to 4. R runs from 0, let's say that is 4, right? So isn't that the bottom half of the circle? And that's the region they're talking about. Of course, we're rescaling everything, and we're saying that and there it is. Now, if I want to integrate, well, that's really simple. You simply r squared over 2 evaluated from 0 to 4, you plug that in, and you proceed all the way down. Here you're going to get r squared over 2 evaluated from 0 to 3, the cosine of theta. That's going to be 1/2 into 9, the cosine squared of theta. That is 9/2. You're going to integrate that with respect to theta, right? And that's going to be what? Isn't that the only way to integrate is to integrate it, store it as 1 plus the cosine of 2 theta divided by 2. So I'm not going over that part. You have questions on that, I'll be more than happy to work out any problem for you in our class discussion. But I'm assuming you know how to integrate since you've taken the 3rd semester calculus, not the 2nd. Evaluate the Cartesian integrals by transforming it into an equivalent polar. So I want to see if you could just transform it first. Integration, I assume you can integrate anything. This says y runs from -1 to 1. Y equal -1 to y equal 1. And this says x runs from negative the square root. By now, hopefully, we're really comfortable with this. I hope you are. And if not, get comfortable with it soon. So y runs from the left side of the circle to the origin. They're talking about this region. Again, this is a big mess. Instead, I could say this is the integral. Let's run d theta, r d theta. Theta is going to run from pi over 2 to 3 pi over 2. And r is going to run from, that's a circle with a radius of 1. There it is. It's simple if you know what to look for and how to do it. And how about this problem? Oh, I forgot an important aspect. What does x equal? R the cosine of theta. There. Here. I'm going to write this as a double integral, and I know that's going to be r d theta. And this right here is simply r squared. Pretty much in good shape. Now I need to know what region are you talking about. Converting just by using formulas is not sufficient. Here they're saying, let's run, x runs from 0 to 3, 0, 1, 2, 3, so we're talking about those, and y runs from 0 to y equal 2x, 2x. So I kind of sort of know how this works. They're really talking about this region. Now I'd rather do rectangular, right? But that's not what they want. So in this case, we know theta is going to run from 0, y equal 2x. So that point is 3, 6. So this is r sine of theta equals twice r cosine of theta. The r's drop off, and you get the 2, so you get what? Those cancel out, and you will get sine over cosine tan of theta equal 2, right? Which means theta is the inverse tangent of 2. Okay, and r runs from 0. If I say x equal 3, by now we know this is r cosine of theta equal 3, r equal 3, the secant of theta. Now the book uses better angles than what I'm using, but I'm giving you all different options. I know you don't like inverse tangent of 2. If it's a standard angle, you could figure out. If not, use a calculator. Just make sure that your angles are always in radians. Degree has no room in this section. And how about if I wanted to know what this is doing? Again, the region. What are they talking about? This says r dr d theta. That's simple. The y is really r the sine of theta. Got it. Double integral. There's double integral. Theta runs, well, I need to know what they're talking about. X runs from 0 to 2, and y runs from 0 to x. In this case, the line is a bit nicer than what I had initially. So now they're talking about this region. I really wanted to do this problem from x to a number, but it's okay. So if I want to use polar, because they're telling me evaluate the Cartesian integral by transform it into an equivalent polar. Well, I know theta runs in this case from 0. If y equal x, that's 45 degrees. And the same deal as what we just did. We know that x equal 3, and we just did this problem, right? So that's going to run from 0 to 3, the secant of theta. And there it is.